We got a good-sized crowd here. I'm going to start in. My name is Bill Higginbotham. I am the president of EA Technology LLC. That's the U.S. office for EA Technology in the UK, and we cover North and South America, the Caribbean, and Bermuda from this office. And I've been doing this for a while, and I've learned a couple of things. So I'll hopefully impart some wisdom today. I know there's some people that signed up for this presentation that are much more knowledgeable than me. I don't know why they're here. I should have them do this instead of me, but welcome. Just some logistics. There's a chat box available. I can't read that chat box and talk at the same time. So put your questions, if you have them in the middle, put them in the chat box. I've got someone who's reading that, and if there's something wrong with the presentation or something, an emergency question, something you really need answered, he'll interrupt me. And then at the end of the presentation, I will be available for as long as you want for any questions. When we're done, we will send a copy of the presentation out to everybody who registered, and the video will be on our website soon enough, as soon as we can process it. So with no further ado, I will move on. One slide on EA Technology, just so we know. So EA Technology was part of the national utility of the UK back when it was formed, and for many, many years we were the R&D group. We solved problems at the medium voltage system and the high voltage system. In 1990, we were spun off into our own standalone company when they privatized the industry and made National Grid, and they made the independent DNOs or distribution utilities, and we kept being the medium voltage reliability experts. So we do a lot of different things. R&D, we make instruments, we do consulting, we have asset management software, we have our own oil lab, SF6 lab, do a lot of low voltage work in the UK. We've got offices in Australia, and Singapore, and China, as well as the US. That's the end of the sales pitch. So partial discharge, what is it and why do we care? And this is an amazingly common question because we don't learn this stuff in school. We don't learn how important medium voltage or high voltage field control is. The electric field control is not something we spend a lot of time on, and it really comes back to bite us in the form of partial discharge. It may be microwatts worth of discharge in the presence of hundreds of megawatts of energy, but it's still a problem. So first thing is, where can it occur? Where do we care? And the physics says that it can occur at any voltage. In reality, it only occurs at, say, 3.3 kV or 4160, if you prefer to say it that way, and higher voltages. So don't be doing PD at your 480 and 1,000 volt levels. You know, stick to your 4160 and higher. It can occur anywhere you have high voltage and you have an insulator. You know, that kind of means everywhere. Where it's real common is metal-clad switchgear, both indoor and outdoor, transformer cable boxes, cable terminations, underground vaults. Cable terminations is probably the most likely area for it, and then indoor outdoor switchgear where you have the high humidity because you've got some outdoor component is real common as well. It can occur in any kind of insulation, whether it's air, oil, SF6, whatever you got. So here's a little video. And I don't know that it didn't play. Okay. Well, of course, these things play perfectly in practice, but they don't play when you're doing the webinar. But this video, which you can see when you get the presentation, this video actually shows the sparks. You can see partial discharge, assuming you can get your head in there and you've got the right lighting. They are visible sparks that occur on the, across the insulation. So what is partial discharge? We all have our own little definition. The Wikipedia definition is it's a flashover of part of the insulation system due to a localized field that's greater than the withstand capability. So what that means is I don't have a complete flashover from line to ground, or line to neutral, or line to line, but I do have it over part of the insulation that might go line to line or line to ground. And that little partial discharge is what's going to cause us problems. To break this down in a very simple way and relate it to Ohm's law, I've got a conductor, I've got a ground. This green thing is some sort of insulation media, and let's say it's molded insulation, I've got an air bubble in it, and that air bubble is not able to withstand the voltage field, the electric field that I'm going to apply to it. Make my math easy, because I'm lazy, I've broken this insulation down into a series of capacitors. All insulation, by its nature, has capacitance to it. And if I say I've got 3 capacitors, I'm going to make all the values exactly the same to make it even easier. And let's say I'm going to 1,000 volts on my conductor. At 1,000 volts, I've got 1,000 volts of on each of my capacitors, and my void can only handle 999.999 volts. So when I get to 1,000, it flashes over, and the act of flashing over makes it go from 1,000 volts to 0 volts as quickly as the capacitance on C1 and C3 will let it. So what happens is C2 wants to collapse to 0. I still have line to ground. I still have 3,000 volts. So what I've got to do is I've got to get 1,500 volts on C1 and C3 in order to balance everything out. And in order to change the voltage on a capacitor, if we remember back to freshman year of college, we would flow current through it. And so what partial discharge is a current pulse that is a result of a voltage flashover. And that's important to remember. We'll talk later about this current pulse and what we do about it. But that's the nature of partial discharge. It's not voodoo. It's not smoke and mirrors. It's a current pulse as a result of a voltage collapse. That insulation might collapse for a variety of reasons, right? It might not be able to withstand the field applied to it because it's just designed wrong, it's dirty, it's whatever. But what happens is when you have an area of different permittivity, so a void has different permittivity than XLPE, and a dirty insulator covered with humidity-laden dust has a different permittivity than the ceramic insulator base. That causes a concentration of field. So you actually get a higher voltage across the field than you would if everything was homogeneous. And that just makes it that much worse. And that causes your breakdown. And once it breaks down, then you've increased the stress on the rest of the insulation. I'm going to talk about 4 different kinds of discharge. Corona discharge is the most common, the least dangerous, and lots of people use PD and Corona interchangeably. They're not. All Corona is PD, not all PD is Corona, to coin a phrase. So Corona is a form of discharge where the insulation that we are discharging across is gas, typically air. And so when I've got an EHV line and I've got a sharp point on a piece of buswork up in the air, I exceed the withstand capability of the atmosphere right around it. So those air molecules break down. They break down to the component parts of oxygen and nitrogen and that, but it's a discharge. The current flows out into the air. Surface discharge is a little different in that it's still at the air insulation border, but that current pulse travels across the surface of the insulation. It doesn't go out into the air much. It might go a little bit, but it's mainly traveling on the surface of the insulation. This is the most common destructive form of partial discharge. You know, with Corona, we're destroying the air molecules, but new air molecules take their place, so it doesn't build up. It doesn't get any worse. It's there. It's annoying. It creates radio waves. It creates ground-level ozone, but it doesn't create catastrophic failure typically. Surface discharge, I've got some defect, causes the discharge, but the act of the discharge damages the insulation even further, which makes it cascade and eventually fail. Internal discharge is where we have something totally within solid insulation. It could be an air bubble inside molded insulation. It could be some sort of cavity. It could be a crack inside the insulation. It could be a gap left in the termination of a cable that was done by an unskilled joiner, those sort of things. This is harder to detect. It creates various different characteristics in surface discharge. It's harder to correct. It's also slower moving, and I'll talk about why. So they're different. You use different techniques to detect them, but you need to understand them both. The last is contact discharge. So this is where I have metal in the high voltage field. And that metal is going to give me a bit of a problem in that it is highly conductive. It acts like a perfect discharge source. But it's not really, again, you're not going to damage insulation with this, so it doesn't lead to catastrophic failure. But because it creates such a high signature, it can hide surface discharge and internal discharge that might be a lower level, and that is a concern. So what causes PD? The number one cause is surface contamination. People don't clean their switchgear. Maybe they just get dust. Maybe they're in a salt environment. Maybe they're in a steel mill and they've got conductive dust. Maybe they're in an oil refinery, whatever. But you get the contamination on the switchgear. It doesn't get cleaned off. And maybe it's conductive, which would then obviously change our field distribution. If it is not conductive, it's still going to attract moisture in the form of humidity. So on humid days, it's going to become conductive. And so, that's why we clean switchgear, purely to prevent surface discharge. Workmanship, poor installation. This is really talking about cable terminations. 70% of the PD failures and the cable failures in the world are due to poor installation. And that varies in what region you're in, but it's a real problem. Manufacturing defects, material defects, you don't get that very often, but you do, occasionally things are built wrong. I've seen extruded cable built wrong. I've seen a variety of things that things separate, you get gaps in it, but it's manufacturing quality is pretty good. Improper application. You're using the wrong parts for the job. So I'm taking something that's supposed to be spaced this far apart, and I'm putting it into a cabinet that's this far apart, those sort of things. Salt spray and salt fog. If you live on an island and you have a power system, I feel bad for you. It's unavoidable that when you get salt spray and salt fog in your power system, you're going to have problems. And some of these island nations and some of these refineries on the Gulf Coast and on offshore platforms, they've got a tough job. I don't envy them at all. That's a big problem. Mechanical damage, things get damaged. For those of you who aren't in the United States, it's a thing we do. We shoot out insulators with a high-powered rifle. It happens, and I don't know why we do it, but we do it. Any kind of mechanical damage can change the field distribution. And then age, things do wear out. Electrical stress does impact insulation, and over time you can get a wear-out mechanism. That can take decades, though. So what happens when we have partial discharge? We have a variety of things happen, and some of them we care about, some of them we don't care, and I'm going to kind of go through this in random order. In the electromagnetic world, right, so we're talking radio waves, light waves, heat, things like that. So light, I can see it. It's a spark. It's visible. It's blue light. It's got some ultraviolet light to it, and that's how I can use a corona cam to find corona, or I can use a corona cam to find surface discharge, but I've got this light. Now, if I'm inside metal clad switchgear or I've got internal discharge, that light's not very useful to me. It creates radio waves, right? If you've ever been out in a lightning storm in your vehicle and you get static on the radio, then you know that radio waves are generated by sparks. It's that simple. I got a green circle around that because we can use that. We can detect those radio waves from a distance and find we got PD on. The bad side of the equation is heat. Infrared radiation is heat. These sparks give off heat. They're very hot. The plasma is hot. And don't get too excited about, oh, it's heat, I can pick it up with an infrared gun. It's plasma, but it's plasma that exists for a microsecond out of every half cycle. So a microsecond out of 8,000 microseconds or 8 milliseconds is a pretty low percentage. So it averages out the heat, and an infrared gun is usually not going to find PD unless it's really in the catastrophic, about to fail, time to run sort of zone. So an IR gun is not a good detector of partial discharge. Moving across, we've got acoustic. So acoustic, some people call it acoustic, some call it ultrasonic. It's all acoustic. These are sound waves that travel through the air. You can pick them up with your naked ear. If they're in the band, you can hear. If it's in the band, you can hear, we call it audio. And if you listen to Corona on a 500 kV transmission line outside of Houston on a humid day, and it hasn't rained for a few days, you're going to hear Corona. And with the naked ear, you're going to hear it pretty good. Now, what also happens is that you get sound waves in the ultrasonic band, which is a lot higher than human range of human hearing. It's 40 kilohertz sort of territory. That is much more common. There's a lot more energy in that band from surface discharge, and so we can use that to detect PD. That's why it's got a green circle around it. In the gases or the chemical world, we're going to take ozone. We're going to take our air for either corona or surface discharge, and we're going to break that air molecules into two. And so it breaks into its component parts, mainly oxygen, mainly nitrogen, and the oxygen turns into ozone, which we can smell. You ever say, oh, high voltage smells? Guess what? It's discharge, and it's ozone generated by the air molecules being broken down. The other half is nitrous oxide, right? Most of the air is nitrogen, and nitrogen forms nitrous oxide, which by itself is not harmful, but it turns into nitric acid in the presence of any humidity. So when you get that nitric acid, that is going to eat through your insulation. And so if you think about surface discharge being the fastest moving, it suffers from the heat and it suffers from the nitric acid. Internal discharge just suffers from the heat, doesn't get nitric acid because it's not in contact with air, and that moves a lot slower. Kind of makes sense. A lot of this is common sense. Moving back over to the left, the electric phenomenon, we have current. We said PD is a current. If I can measure that current directly, that's fantastic. And the other thing is TEV, or transient earth voltage. And this is a voltage that is induced on a grounded metal enclosure, say metal-clad switchgear, shield on a cable, things like that, tank on a transformer, due to discharge inside. And if we can detect that voltage, non-contact from the outside, we've got a much safer way of finding PD. So that's kind of the breakdown of what happens with partial discharge and what's good and what's bad about it. Variety of different test techniques. So we've got acoustic testing, and that is ultrasonic or acoustic. But basically, I'm listening. I'm keeping the doors closed. I'm not connecting to anything. I have no direct connection to the power system. I'm listening through louvers and vents. I may use contact sensors. I may use a parabolic dish to look from the ground up to overhead assets. Clearly, that's non-invasive and is a great technique for finding any kind of surface discharge. TEV testing, we're going to place a TEV sensor on the outside of the cabinets, the outside of the transformer, the outside of the cable. Non-invasive, don't need an outage, can't hurt the cables, can't hurt the switchgear, and it's perfectly safe. RFCT testing, this kind of dances the line between invasive and non-invasive. We take a split core radio frequency current transformer called an RFCT or an HFCT, the same thing, and we attach it to the cable ground straps. Some people put them on conductors. I don't like them on conductors. Put them on the ground straps where they're inherently safe. Put them right down by the ground bar and bring your connectors out to a safe spot. Now I can test that cable anytime I want. I don't need to take an outage. I can test it every day if I want, and I can trend it if I want. I can put full-time monitoring on. I can test it once every 3 years without taking an outage. So installing those, once they're installed, then that's really non-invasive. And the last is RF testing or UHF testing. I'm able to pick up radio signals generated by the PD. Obviously, I'm listening for radio signals. So all these are non-invasive. They do different things, and they work good on different types of discharge, so I may do all of them in order to find discharge because I don't know what type of discharge I've got. I'm going to start with surface discharge because it's the most common, it's the fastest moving, it's easiest to find, but it's also the most likely cause of failure. So we're going to monitor it centered around 40 kilohertz. These waveforms are kind of broadband. They go from 30 to 50 kilohertz rather, and 40 kilohertz is just a convenient point for us. They go through air really well. They can travel through liquids and solids, not as well, but they can. In severe cases, there will be a fair amount down into the audio band that you can hear. Might depend on your hearing. Mine's terrible. I don't hear it so much, but these younger guys, they got an advantage. What the instruments do is they'll detect these bursts, they'll measure them, they may provide phase result plots, they may provide various different characteristics for the user, but most all of them also take the signal and by a process called heterodyning, drop the signal center frequency down into the audio band. And what's nice is it doesn't change the nature of the audio, and I can listen to it. And your ears are incredibly sensitive and incredibly discriminatory. You can hear the same singer sing the same song on 2 different albums, and you can tell the difference. It's hard to get a computer to do that. So listening is always going to be valuable, and if you're not doing that, you're not doing ultrasonic testing. When you're doing a survey, you need to think of some things. The level of PD and the transmissivity of the air for ultrasonic energy varies with humidity. So we want to make sure we record humidity, and if you have an instrument that actually records humidity in the same survey and all that, you're taking the data, that's even better. So when you come back a year later and then the humidity is dramatically different and the PD is dramatically different, you've got some cause and effect there. Temperature doesn't have much effect on PD, but it does give you if say you have a crack and that crack expands when things heat up, that's going to give you perhaps more discharge. It has very characteristic sound. Once we've brought it down into the audio band, it sounds like, amazingly enough, what you would expect it to sound like. It sounds like crackling, buzzing, arcing, sparking, bacon frying, exactly what you'd expect. In the beginning, it may come and go with humidity. It may come and go with voltage, but as it gets worse, it's going to be less intermittent. And then the bad news is the number you're going to read off the instrument doesn't mean much. The severity of the discharge is not necessarily related to the noise. So I put my hand up in front of my mouth and keep talking. You will notice, you will measure a reduced level, even though the discharge had not changed. So we don't know where this discharge is occurring. Is it on the front of the switchgear? Is it on the back? Is it behind the panel? Is it buried? Can vary. But wherever it's located isn't going to change over time. So let's track it over time. Or if I've got 6 different cabinets that are all built exactly the same, and I've got one level that's a lot higher on one than the other 5, that's trending or comparing to other things. So we want to do that. I'm going to try and play an audio here. Hopefully it'll work better than the video. This is real recorded PD after it's been heterodyned into the range of human hearing. Let's see what happens. Okay, hopefully you heard that. That's what it sounds like. And we can supply, we've got some wave sound clips on our website that you can review. So the environmental factors, I talked about the moisture playing a factor. One thing you can do is use that, not just know about that, you can use that as a tool. So if you're doing, say, full-time monitoring, where you're tracking humidity and the ultrasonic level, look at this chart. The red is the ultrasonic level recorded on one particular sensor in a monitoring system, and the blue is the relative humidity of that room. Well, if it's going up and down at the same time the humidity is going up and down, if you're concerned that the ultrasonic stuff you're listening to is not PD, why would it vary with humidity? If it's a light that's buzzing, that light doesn't change with humidity, and or a battery charger doesn't change with humidity. So it's a good indication that you've got something real going on. This is from a virus, a vaccine manufacturer in Pennsylvania that we recorded this. TEV, now TEV is a bit odd. It's probably the least believable thing I'll talk about today, but TEV is a voltage that appears on the outside of the switchgear as a result of discharge inside the switchgear. So this picture here, I've got a piece of bus cabinet, and I've got a bus bar sitting on insulators, and I've got a defect in my insulator. I've got that void. So I get a discharge, I get this current pulse that goes down the insulator, and it hits the inside of the cabinet. It can't go through the cabinet. At these frequencies, it won't go through a cabinet, won't go through copper, won't go through even foil shield on a cable. It has to travel on the surface of the metal. So what happens is it travels all around the inside of the cabinet trying to find a path to ground, right? It's a current, wants to go to ground. And what it does is it eventually finds a gasket or a joint or a door or something, gets the outside of the cabinet looking all over for a place to go. It finds a path to ground, and that path to ground is the grounding of your switchgear arrangement or the ground strap on your cable or whatever it is. That's a great low impedance ground at 60 hertz. Damn near zero at 60 hertz. But 60 megahertz, it's not so great. Big, thick bus bars are really bad RF ground sources. So what happens is we have a bit of an impedance. Now we go back to Ohm's law that I have a current across the impedance, I get a voltage. And so what I'm going to do is I'm going to measure that voltage with a voltmeter. A very fancy voltmeter I'll give you, but it's got a capacitive probe in the front. Your body and your hand holding onto it forms a capacitive sink as the other lead of the voltmeter. And this voltmeter has to be able to sample in the nanosecond range to pick up these things that are microseconds long, pick up waveforms, measure the peaks, capture the waveforms, capture the phase resolve plot, do all that at these really high speeds and really low levels, measuring microseconds or microvolts and that are microseconds long, and I'm doing it in the presence of hundreds of thousands of volts and hundreds of megawatts. So it's not the easiest thing to pick out, but the right instrument will grab that for you. The first things we want to look at once we've done a TEV measurement, and this is the scourge of PD measurements is that all these lines are blurry on purpose. There are no straight lines or solid lines in PD testing. But what I've got across the bottom here is a level, which is the voltage, in a logarithmic scale where if I go up by a factor of 10, it's 10 times worse. So from 0 to 10 is 10 times worse, 10 to 20 is, or 0 to 20 is 100, 0 to 30 is 1,000, etc. And then I'm also going to look at the pulses per cycle. Yes, this says pulses per second. It should be pulses per cycle. I apologize. If you look at a sine wave and say, well, I discharge at my peak voltage on the top and I discharge my peak voltage at the bottom, then I'm talking about 2 pulses per cycle. Maybe it's bad enough that I can charge, charge, and discharge again in a half cycle. I got 4 pulses per cycle. That's pretty reasonable for internal. And that's where you see this red box. Internal, our levels, you know, anything below 10, 15 dB, 20 dB even, I'm not that excited about. I get 30, 40, 50, 2 pulses per cycle. I'm really looking at internal discharge. Now, if you talk about surface discharge where I have this treeing, and every branch on that tree can fire at a slightly different voltage, I can get multiple pulses per cycle, more than 4 to 6. I can get 10, 15, 20 in one cycle. So I would say that this is in the area of surface discharge. Got a really low level, I'd say that's nothing significant. If I've got a really high pulse per cycle count, then that tells me I'm probably listening to some sort of interference, radio waves, fluorescent lights, various different things can create background interference. The last is the possible contact discharge. So contact discharge or floating metal discharge is where I have metal in the high voltage field. And that metal acts like a perfect TeV source and creates a lot of discharge. Won't necessarily lead to failure, but it masks all the lower level signals and makes it harder to see. My favorite example of this is a guy that we had a set of switchgear with full-time monitoring on, brand new switchgear, brand new cables, energized the switchgear, everything's up and running. A couple days later, we got the monitor running, and in one cabinet, we had 50 dB, 50 pulses per cycle. Shut it down, what's going on? We opened up this cabinet, it was a cable compartment, and inside the cable compartment was a Home Depot bucket full of tools. And because the tools were in a bucket, they were insulated, and but the metal on the tools created this massive discharge effect, which prevented us from seeing anything smaller. So just a quick summary on surface and internal discharge before we move on. Internal discharge is not going to be affected by humidity, whereas surface discharge would. The pulse counts are different. You're never going to hear internal PD, and TeV is your best measurement technique. For external PD, it's ultrasonic. We don't know what we're looking for, so we're going to do both tests. And in order to do a test, you're going to hold the equipment tight up against the ground or against the metalwork of the switchgear, because I want to measure that voltage, as opposed to an ultrasonic test where I'm going to be looking for sound waves traveling through the air. So I'm going to hold it away and I'm going to move it around to the louvers and air gaps. Cable discharge is, like I said, very common. It's a real issue in lots of places where I have a defect, right? So I've done workmanship in the field. I had a guy in a trench terminating a cable. If that isn't done right, you can get a defect, and that defect is not immediately visible. It can cause a lot of discharge. And places that have had booms in the oil industry or the offshore industry or that, where they're making a lot of cables in a short time, they get people that are less skilled and less trained, they tend to have more problems. It always makes sense. Here's an example of a cable, and anybody that's on this screen that's a cable expert is absolutely horrified. You've got this cutback, which is terrible, and you can see the insulation's eaten away and it's flashed over. This was not caught ahead of time. This is after the fact. Nice thing with cable discharge is I can look at the ground strap. Discharge goes from the conductor to the ground strap if it's inside the shielded portion, or it goes, if it's outside the grounded portion, there's still this current is traveling down the conductor. The conductor acts like an antenna, and it radiates into the shield and goes down the ground strap. So if I can count the electrons going down that ground strap, then I can determine whether I've got PD or not. So that's PD. I spent about half the time talking about PD. That's good. That's what I intended to talk about. Now I'm going to crank through our instrument, and I'm going to talk about ours because that's what I have familiarity with. There are other makers, there are other products, there's similar things. Obviously, I'm going to be biased toward mine, but this is not not that far out for anybody who's using a piece of equipment. These techniques are all relative. Ours is called the UltraTeb Plus 2. It does a variety of things. It does ultrasonic, TEV. You can connect to RFCT. We're doing PD and cables. It has built-in temperature and humidity probe, and you can also plug in a UHF directional antenna and pick up radio waves. Built-in classification is a good thing. We believe that it helps as opposed to just giving the customer a very simple screen. They want the data, they want numbers, they want something they can see, but they also want a little help because ultrasonic testing or TEV testing isn't something you're going to do every day. So, if it comes up and it says here that it's possible surface discharge, use the ultrasonic, or here and on the ultrasonic screen it may see PD or noise. These sort of things are built-in algorithms that help the user interpret the data, but we're still going to give you all the data because we're technical people. We like data, but we also like someone to tell us what it means. Phase resolve plots are the number one thing. If you're ever considering buying equipment and it doesn't have a phase resolve plot, you're really think about that hard. PD occurs in this part of the sine wave. Nice, as you're leading up to the peak, it would make sense. As I get to the peak voltage is where the field's the strongest. Occurs in a positive and negative half cycle, so I can have 2 pulses per cycle or 2 groupings of energy. If I look at this phase resolve plot, this is from each green dot is one event, and it shows the phase angle and the amplitude. And I let that run over a few seconds. I've got a lot of dots, and I can see I've got 2 groupings of energy that are half a cycle apart, and that's an indication that whatever I'm looking at is synchronous with the power system and caused by the power system. And so that's going to give me a real indication that I'm not listening to a fan or a light or a freight train even. It's something caused by the power system. That's going to be a good indication that I've got PD. The fact that the shape of this curve and if you had a vertical line that said it was always occurring at exactly the same phase angle, PD doesn't occur at exactly the same voltage, so it doesn't occur at exactly the same phase angle. That would tell me I'm looking at something electronic. If I see 6 vertical lines, I'd say I'm looking at an inverter or some sort of 3-phase drive. Those sort of things are going to help me determine what I'm listening to. Because we really are listening to ultrasonic energy or picking up TEV. Those are not direct measurements. We're inferring from those measurements that PD exists. So that's the value in the phase resolve plot. If you call me up and say, I've got a +2, I took a measurement and it's 30 dB. First question I'm going to ask you is, what is the pulse per cycle count? It's a TEV test. The second question is going to be, what does the phase resolve plot look like? Without those 2 pieces of information, you're guessing. Temperature and humidity. We have a temperature and humidity probe that you can plug in. That's nice. It's recorded with all the data that you have from your substation, and it's trackable and trendable over time. If you're going to take a TEV measurement, it's just like this. You're holding the instrument tight against the outside of something where there's high voltage inside. So don't do it on the upper cabinet, which is all instrumentation and protection control. Hold it down on the breaker cabinet, or on the back, on the cable door, or on the vault of the transformer, or on the tank of an instrument transformer. That's where you're trying to see if something going on inside. Takes a few seconds to settle out, and then you can record the data, review the data, depending on what information you need. I talked about our interpretation mode. We've got, ultrasonic here. It tells, because of this pulse count, 28 pulses per cycle. I told you half hour ago that means it's probably ultrasonic, probably surface discharge. So it tells you use ultrasonic. That's more sensitive than TEV. Here I've got a nice high level. I've got a pulse count that's just under 1. That's likely internal discharge. Here I've got number. It's pretty high, but my pulse per cycle count's too high for PD. So I'm going to say that's probably noise. Just trying to help you along. You get phase resolve plots from TEV just like you do for ultrasonic, and there's some characteristic plots. This one is not. This is actually off my neon beer sign that I use for creating screenshots. Neon discharge, not partial discharge. But you see we've got 5 pulses per cycle. That's in the range. I'm below my 20 level, so my number's green. And I've got a phase resolve plot. I've got 2 groupings, but it doesn't look like what I would typically expect. Waveforms. You want to see waveforms that are fast in their rise time, have a little bit of a logarithmic decay to them, and aren't all over the place. So you may have something that's caused by the power system that isn't PD, and the waveform is what's going to tell you the difference. So that's TV. For ultrasonic, you've got a variety of different probes. You've got a built-in probe, which is just handy because you got less cables to deal with. You've got a flexible probe you can use, and a parabolic dish. Parabolic dish is good for 2 things. One, it's good for looking at outdoor gear from the ground. You know, you can get a lot closer, a lot more effectively closer. But it's also if you need to stand off a cabinet. You know, we've had situations where, okay, I've gotten some PD. I don't want to open that cabinet door. I've got some indication of my PD because that cabinet door's got, got compromised insulation. I can use the dish. I can stand back, safe distance, open the door, have someone else open the door with an arc flash suit on, and find that PD. We've been very successful with that. The contact sensor is your sensor of last resort. Sometimes you don't have an air gap. You've got outdoor gear. It's got a weather strip. It's around the door. It's got no vents or louvers. You don't have an air pen. So you use a contact sensor, and that just connects to the door on the outside and turns the whole door into a sensor. Now, as you might imagine, if I'm looking for ultrasonic waves that are, the level of your eye blinking to vibrate a steel door in a cabinet, it's not going to vibrate very much. So you need a really sensitive sensor for contact. And we've got that because it's so sensitive, you're going to have a little more impact of background noise like wind and things like that. Ultrasonic detection through louvers or gaps, that's great. You want to find that. If you don't have louvers and gaps available, you're going to use the contact sensor. I've already talked through that. Here's the ultrasonic screen. Tells me what sensor I'm using, tells me the level. The level's turned red because it's a high level. I've got my algorithm telling me it's PD or noise. I've got my phase resolve plot, and I'm listening. I'm wearing the headphones all the time. Here's an example of a phase resolve plot that is clearly not phase resolved. It's random. It's noise. Even though I've got a level that's 1,000 times worse than this one, I'm much more excited about the one on the left because it says it's PD, and my phase resolve plot looks like PD. This one probably sounds like a high-pitched squeal, so I've got audio tells me no, algorithm tells me no, phase resolve plot tells me no. This is not PD. Here's an example of surface PD detected with ultrasonic. Here's where we had found some ultrasonic signature with the door closed from the gap that said this could be PD. Went back, stood back, and ran the parabolic dish. It has a laser sight in it. Ran it up and down all the different terminations until we found the highest level of energy. And if you look right here, you can see the red dot from the laser sight, and right next to it is that white powder. It's very characteristic of PD. None of the other bushings have any white powder residue. What happened is the guy terminated the cable. He terminated a little bit short, but he had a crowbar so he could make it fit. And in doing so, bent the bushing, bent the rubber boot. There was an air gap. That air gap was not the same permittivity as the rubber, caused the discharge. The whole inside of that boot was covered with white powder and tracking. And they pulled a new cable, replaced it, worked fine. I went up and I tested it. It was dead quiet. Ultrasonic measurements, I think I've beaten this one to death, but basically you're wearing the headphones, you're listening, you're looking through air gaps, and you're watching the screen. Cable PD measurements, the challenge with PD cable measurements is you've got to get the RFCT or HFCT on the cable, right? Those cable terminations are not always visible. In Europe, IEC style switchgear has the cable grounds outside the cabinet. US style switchgear has cable grounds inside the cabinet. Riser poles, obviously, you can get to, and ground straps on transformers and things like that you can get to, but the individual cable terminations can be difficult. Here's an example of the RFCT or HFCT connects to the unit. It's a split core. We can open it and close it and install it on whatever we need. So here is a hot stick mounted RFCT on the gear to give us a little more separation. There they are mounted on it. You know, safety is a challenge. We you know, back in that lower picture, we went in like Superman, and we went in and hooked those cables, those RFCTs on the cables. Don't do that much anymore. It's the big push now is permanent RFCTs that come out to test points, or they use the HFCT on the hot stick, or they, you know, sometimes on riser poles and that, the grounds will come down low enough where you can grab it. But not much done that way. You can also shut off power, connect everything, re-energize, and do that, but it takes time. UHF, I touched on this a little bit. So radio waves are great. Radio waves come out of sparks. It's just part of the nature of the physics. If I can get out there with a piece of test gear and measure that, I can see stuff that might be internal. So if you look at this bushing here, if I had PD inside that bushing, which is very common, it's inside, so I'm not going to create ultrasonic. It's not inside a metal box, so I can't use TEV. It's not necessarily going directly to ground, so a ground strap isn't really going to help me very much with an RFCT on it. UHF is my best way to go. And what's nice is I can walk around the substation at a standoff distance and find stuff in exposed air insulated switchgear pretty easily. Ours in particular is designed to ignore corona. So that the instrument rolls off below around 250 megahertz, so we avoid seeing corona discharge because we want to ignore that. That's not destructive, so we want to ignore it best we can. All right, so here's our UHF system. It's an antenna and an adapter for the box, and it's a very directional antenna. It's got about a 45-degree cone, so you can walk up to individual insulators, A, B, C. I used this in Chile, and I was able to tell them which one of their insulators needed cleaning just by picking up the UHF emissions from the insulators. Variety of different screens available with that. We've got a spectral plot if you like the EMI type thing. 3D phase result plot I find the most useful, and we've got the conventional phase result plot. So now the fun part, some examples, some things we've seen. Let's try not to judge the people who did this too harshly. We've all made mistakes. So here's a couple trifurcated cables, and on all of these, the shield cutback is way too low. I don't know whether they didn't have instructions, didn't understand the instructions, but you can't have these cables that close together after the cutback. You basically got two cables touching, almost touching. You've got the white powder, you've got the tracking. User error here. Here's an example from one of my island customers. The poor guys are very close to the water. They have lots of salt. They have a lot of humidity, and this is not very old switchgear. It's very new. I took this picture myself. It was in a pile of other things that they had replaced. Tracking, treeing, you see the white powder. You see the copper is also turned a lovely shade of green. That is due to the nitrous oxide in the air. Nitrous oxide will cause the copper to discolor. It'll cause steel to rust. If you're ever in a cabinet and all the steel bolts are rusty, nuts are rusty, and there's no evidence of water, or even weirder is you've got rust at the top of the cabinet and not at the bottom, why? You should have rust at the bottom where the water might accumulate. This is that cabinet that I was talking about. Here is deploying the wrong parts for the job. There's nothing wrong with these boots. They're just not made to be this close together. By being this close together, we cause a field stress concentration, and we've got discharge. We've got tracking, we got white powder, we've got rust. All the bolts are rusty, and if I were able to zoom out in this picture, you'd see the bolts at the bottom of the cabinet are as clean and dry and non-rusty as can be. So that's a good indication. If you don't see anything else, why is it rusting? Here's an example of someone who just didn't clean the switchgear. This was in Florida in a high humidity, high dirty environment, and this brace was there to keep this bus bar from pretzeling if there was a fault. And what happened is they didn't clean it, and these horizontal surfaces between the phases collected dust. The dust collected humidity, became conductive, changed the electric field distribution, and caused this massive discharge. This was screaming out ultrasonic. You almost didn't need an instrument to hear. A customer went out with no training, turned on the unit, put on the headphones, and boom, I found PD and fixed it. And they got rid of the brace, wrapped this in high voltage tape, and went on their merry way. I haven't had a problem since. Here's a tricky one. This is one of my favorites. This is an installation where they had the unshielded jumper cable, and those of you who have worked with unshielded jumper cable, you know it's terrible stuff, and especially for PD. It may withstand the voltage, it may do a high pot, but it doesn't withstand the field. And so in this example, they've got a brace that comes out here, and that corner of the brace is resting on the round edge of the cable, and that small geometric point is causing a discharge. And even though you could high pot this, you could measure it, you could do whatever you want, it still caused discharge. And it did it from the minute it was energized until they took it out of service. And they had 13 identical cabinets, and you can see every one of them was discharging. Here's the cable. This is after about 4 months of operation. This would not have lasted a couple of years. But again, a lot of people looked at this and said there's nothing wrong with that, including the switchgear manufacturer. Nothing wrong with that installation. It's because we're not used to it. We don't use it all that often. That's what they have. Here's an example of internal discharge where it has eaten the hole. So this is a cast resin CT. It's been cut in half, and the conductor here has been removed. But it ate right through that resin. That resin's hard stuff. This may have taken decades, but it cut through it and was on the verge of failure. This would move slower than service discharge because we don't have the nitrous oxide. All we have is the heat of the spark. And each time that goes, it may kill a couple molecules of insulation, and it takes a while to eat a channel all the way through. Here's an example where they had these little plastic boot things, which I've never seen anywhere else, and now it's causing a discharge. Even though I had it was just an insulator, but an insulator in the wrong spot was causing discharge. And a nice phase resolve plot. If I were to play the sound clip, it sounds just like it should. Big high difference, 35 dB versus 0, so 1,000 times peak to the noise ratio. That's a nice clean phase resolve plot. And there's the sound. So here's an example that we're getting corona and surface discharge. Now corona, because of the nature of how electrons want to move, occurs more on one polarity versus the other. And that's why we see a bigger point here, but only one. And so what we get is a more 60 hertz undertone and a very characteristic waveform. So we can tell that we've got surface discharge, or corona discharge, not surface. Now in this case, they had both. They had to clean up the corona, and then once they did, they could see that they had surface discharge as well. So that's why we want to know that we've got corona, so we can get rid of it and have it prevent us from seeing that we had surface discharge as well. Here, and I'm not going to play the sound clip because it's really annoying, but look at this phase resolve plot. The numbers are huge, 50, 60 dB. If I went just on a number, I would think I've got a massive problem. But looking at it, it's not related to the power system at all. It's just a high frequency random pulse as a result of whatever's going on inside this AC to DC converter. Very briefly, hit you with it there. Here, looking from the ground with TEV, we basically put TEV on the ground strap from these points, and we could see a phase resolve plot as a result of bad termination on this cable riser. And so it was internal. We couldn't pick it up with ultrasonic. But, well, no, I'm sorry. I'm lying to you. This is an ultrasonic plot with the dish, and it's finding PD. The algorithm says it's PD, and the phase resolve plot looks like it's PD. Don't know why I say TEV there. Here is an example of the UHF in action. So this is some weird Australian switchgear. I've never even seen anything like it. But it's not enclosed in metal. It's actually behind a fence. So I can't do TEV. It's something occurring inside, so I can't do ultrasonic. There's no way to get to the ground straps down here. I could have picked it up on these ground straps, but they don't have RFCTs installed, so I can't get in there. It's not safe. So using UHF, I was able to narrow down in the directionality. I was able to figure out which one of these things had the PD in it. And I got a nice phase resolve plot, 2 groupings, half a cycle apart, very concentrated, nice and clean. So I was able to find out what was going on. So that's the end of the presentation. I'd like to open it up now for questions, and my associate George is on the air. George, we got any written questions we want to address first?
Yeah, we have can you hear me?
Yep.
Okay, so we have on the pre-survey questions, when we registration questions, the recommended frequency of PD testing.
So yeah, the recommended frequency is related to your own tolerance for risk, but very common to be done annually. And if you are doing annually, tend to do it spring, fall versus winter, summer, so that you get more even humidity. Some people do it every 2 years. Some people do it every 3 years. You know, what I would do is, if my resources are really critical, I would do it every year. If I've got some stuff that's less critical, I would look at that less frequently, you know, maybe every 2 years.
Okay. Another question, actually it was kind of two related questions. Someone's asking about, you know, how do you determine the severity of corona? And then they were asking about the standards for decibels, kind of both related.
Okay.
Tables.
So the levels for corona or any kind of discharge, what we do is we kind of give you a value. It's a standard recording. There is not a wealth of data in standards in terms of what levels you should look for. The NETA 2019 MTS standard has values for switchgear testing and what values you should take action at, and those happen to be the numbers that we have where we turn from red to yellow to green. Most people use those sort of levels, and you can change them, but if you look at the levels where on TEV at 20 dB I go from green to yellow, and 30 dB I go from yellow to red, and with ultrasonic you really want to look at anything that you find real PD. So
next question, if I use a high frequency current transformer to test cables through the ground strap, can I use the partial discharge TEV interpretation?
It's a good question. So they are going to be similar, yes. You're looking at the same sort of pulse count, you know, internal discharge is internal discharge, whether you're measuring with TEV or RFCT. So yeah, you can use the same interpretation to some extent. You're not going to get surface discharge with the RFCT typically, so you're not going to get those higher frequencies. Also, one thing you can do when you're testing cables, you can do a TEV on the sheath of the cable, right through the plastic onto the shield. If you're very close, say you do it right at the outside of a switchgear, it will tell you whether it's PD in the cable or PD in the switchgear.
How do I separate noise from partial discharge readings? I think you kind of covered that.
I tried to cover that, and that's the eternal challenge for everyone. Phase resolve plot is your number one tool for that.
Okay. Back to cables again. When you say ground strap, I'm assuming you're talking about the cable shield. Does it matter whether the shield is grounded at one end or both ends?
That's a good question as well. Yes, I am talking about the strap that is attached to the cable shield. If it's attached on one end, obviously all the current is going to flow down that one end. If it's attached on both ends, it is going to divide. And depending on where it is, if it's closer to one end versus the other, it's going to go one end. So if you have the cable that's very long and it's grounded at both ends, I would test it at both ends, redo the test on both ends. If it's relatively short, you can get away with testing it on either end. And obviously, if it's grounded on one end, you're only going to test that end. Good question, though.
Okay. I had a few people ask about costs. If they could just email us, we'll deal with that separately. Next question. Can I use the UHF sensor at cable terminations and joints? That last slide, I think you kind of covered that.
Yeah, you can to some extent. I mean, if it's in the shielded portion, it's not, the UHF is not going to get out. But if you're looking above the shield where it's been cut back, yeah, you can get UHF from that.
Okay. This is more specific to our instrument. Does the test equipment have the ability to save data, screenshots, and audio files?
Yes. Yep. And especially what's really nice is the audio file. So you get a sound clip. That's really good. You can connect the unit to your phone and email it to your resident expert, because not every one of your field crews is going to be an expert in listening to the sound. But then you can also archive it. And before I go out and do a test next year, I'm going to review last year's test, and if I've got any sound clips, I'm going to listen to them. Hey, that sounds a lot different than last year. Why? You know, it's a bit of a detective move instead of your standard test and report mode.
Yep. There was a cable question. Oh, can you determine the location of a PD defect in a cable?
Yes, not with the instrument that I demonstrated, but with another product we have, we do that. It's very common on offline testing to use basically like a TDR type function to determine where the discharge is. What we do is we look at the first pulse and the second pulse. The second pulse is actually reflected off the far end, and we look at the time. By looking at the time, we can determine how far away it is. Now, the problem is when you're doing an online test, it's not as easy to do as an offline test. So you might imagine an online test has a higher noise floor, and because your shield might be connected at both ends, you have a lower reflection. Right? Reflections are determined by the impedance mismatch. So I have less of a mismatch, so I have a lower reflection and a higher noise floor. We find the online tests only about 25% of the time can we actually find the distance to the fault, whereas that might be a lot higher in an offline test. Idea here is I've got 100 cables. I test 100 cables. I find 5 of them have PD. Those I might want to do an offline test on.
The rest of their questions are more, very granular, specific to us. I just want to mention to everyone that we'll come back to you individually with any of those in the next 24 hours. So that kind of covers it. We're right at the end of our time, Bill.
Okay. Well, I mean, if anyone has any questions they'd like to ask now, I'll be glad to answer. Okay.
All right. One again, more specific to us. How often does the equipment need to be calibrated?
Yeah, well, once a year, and the instrument keeps a date in it, and it'll tell you after a year that it's due. Okay. I see a question. I'm looking at some question. What is the white powder left after discharge? That's a question near and dear to my heart. I got that wrong in a paper about 6 years ago. So what it is it's actually the components of the insulation as it's being decomposed. It pulls the fillers and that out of the insulation. And I don't know the exact chemical name for the white powder, but it's basically the insulation broken down. All right. Well, I appreciate everyone spending the time. I hope you've learned a little bit. And, if you have any questions, you can contact George or I directly. We're here, via our website or via our email. And we'll be sending the presentation out, and we'll be posting this video online as soon as we can process it. All right. Thanks again.